Welcome, fellow engineers and tech enthusiasts, to a deep dive into one of the most critical aspects of modern cloud infrastructure, securing Kubernetes. As Kubernetes continues to dominate container orchestration, the need for robust security measures has never been more paramount. Today, we're not just talking theory, we're going hands-on to harden a cloud-based Kubernetes cluster, focusing on three foundational pillars: role-based access control, network policies, and secrets management. Imagine your Kubernetes cluster as a bustling city. You wouldn't leave the city gates wide open, nor would you give every citizen a master key to every building. Similarly, in Kubernetes, you need to control who can do what, where traffic can flow, and how sensitive information is protected. Ignoring security in Kubernetes is like building a magnificent skyscraper on quicksand. It looks great until it all comes crashing down. From data breaches to unauthorized access, the risks are real and can have devastating consequences. Our goal today is to equip you with the practical knowledge to minimize these risks and build a more resilient, secure Kubernetes environment. We'll explore core Kubernetes features, illustrate their implementation with clear examples, and show you exactly how to apply these concepts in your own cloud deployments. Get ready to transform your Kubernetes security posture from vulnerable to hardened. Our first defense mechanism is role-based access control, or RBAC. Think of RBAC as the security guard and access badge system for your Kubernetes city. It dictates who, a user, a group, or even an application running in a pod, can perform what actions, like creating a deployment, listing pods, or deleting a service, on which resources, pods, deployments, services, within your cluster. The guiding principle here is least privilege, granting only the necessary permissions for a task to be completed, and nothing more. Why is this so crucial? Because overprivileged accounts or applications are massive attack vectors. If an attacker compromises a pod with excessive permissions, they could potentially gain control over your entire cluster. RBAC empowers you to precisely define and enforce these boundaries, creating a more secure and predictable operational environment. It's the cornerstone of internal security within your Kubernetes cluster, ensuring that every component and every actor operates within its defined scope. To implement RBAC effectively, we need to understand its core components: service accounts, roles, and role bindings. A service account is essentially an identity for processes running in a pod, much like a user account for an application. By default, service accounts have minimal permissions. A role is a collection of permissions that can be applied within a specific namespace. For example, a pod reader role might grant permissions to get, list, and watch pods. Finally, a role binding connects a service account, or a user/group, to a role, effectively assigning those defined permissions to the service account. This modular approach allows for flexible and granular control. Our example will create a secure app NS namespace, an app pod reader SA service account, and a pod reader role that only allows reading pods. The read pods role binding then links the service account to this specific role, confining its power to just observing pods within that namespace. Let's put RBAC into action. We'll deploy a backend app into our secure app NS namespace, and crucially, we'll configure its deployment to use our app pod reader SA service account. Once the backend pod is up and running, we can use kubectl exec to run commands from within that pod. We'll first attempt to list other pods in the namespace. Given its pod reader role permissions, this command should successfully return a list of pods. This confirms that our service account has the intended read access. Next, to demonstrate the principle of least privilege, we'll try to list deployments from within the same backend pod. Since the pod reader role does not include permissions to list deployments, this command should fail with a permission denied error. This clear distinction visually illustrates how RBAC effectively limits the scope of an application's capabilities, preventing it from performing actions beyond its designated responsibilities and significantly reducing its attack surface. Moving on to our second pillar, network policies. If RBAC controls who can do what within the cluster's API, network policies control which pods can communicate with which other pods or network endpoints. Imagine them as a highly configurable firewall living right alongside your applications within Kubernetes. In a large cluster with many microservices, preventing unrestricted communication is absolutely vital. Without network policies, any compromised pod could potentially communicate with any other pod in the cluster, leading to devastating lateral movement for an attacker. Network policies allow you to segment your network at the pod level, creating isolated zones and enforcing strict communication rules. This dramatically reduces the blast radius of any security incident, ensuring that even if one service is compromised, it cannot freely interact with others. It's about building a robust internal network perimeter for your applications. The safest starting point for network policies is a default deny posture. This means that by default, no pod can communicate with any other pod or external endpoint unless explicitly allowed. This is implemented using a network policy that selects all pods in a namespace, with an empty pod selector, and specifies empty ingress and egress rules. Our default deny all policy will apply to every pod in our secure AppNS namespace, effectively shutting down all incoming and outgoing traffic initially. This might seem extreme, but it's a critical security measure. From this secure baseline, you then precisely open only the necessary communication channels, adhering strictly to the principle of least privilege for network connectivity. This forces you to think intentionally about every single connection your applications need, greatly enhancing your overall security posture. Now, let's observe the impact of our default deny policy and then selectively open up communication. We'll deploy a frontend app in the same secure AppNS namespace. Initially, with the default deny all policy in place, if our frontend pod tries to curl the backend service, the connection will time out, demonstrating that all traffic is indeed blocked. Next, we'll apply an allow frontend to backend network policy. This policy specifically allows ingress traffic to pods labeled app, backend only from pods labeled app, frontend on port 80. After applying this, the curl command from the frontend to the backend will now succeed, proving that we've selectively opened that vital communication channel. But there's another crucial piece, DNS. Without explicit rules, even DNS lookups will fail. We'll then apply allow egress DNS, a policy that permits all pods to communicate with the cluster's kubectl service on port 53. After this, lookup google.com from the frontend pod will finally succeed, illustrating how to carefully manage egress traffic for essential services like DNS. Our final pillar focuses on secrets management, how to handle sensitive data like API keys, database credentials, and configuration files containing confidential information. In a containerized world, simply hard-coding these into your images or putting them in plain text config maps is a recipe for disaster. If your container image is ever compromised or your config map viewed, your sensitive data is exposed. Kubernetes offers a native resource called a secret to store and manage this data. Secrets are designed to be a more secure way to inject sensitive information into your pods, preventing them from being accidentally committed to source control or exposed in logs. However, it's crucial to understand their capabilities and limitations. Kubernetes secrets store data as base64 encoded strings. It's important to note that base64 encoding is not encryption, it's merely a way to represent binary data in a text format. While the underlying ECK database in a cloud Kubernetes cluster is typically encrypted at rest by the cloud provider, Kubernetes native secrets themselves are not encrypted within ECK by default at the application layer. Pods can consume these secrets in two primary ways, as environment variables or as mounted files. Our app API key secret will contain base64 encoded values for API_key and DB_password. When mounting as environment variables, the Kubernetes API server dynamically injects the decoded secret values into the pod's environment. When mounted as a volume, the secret becomes a temporary file in the pod's file system. While convenient, this lack of inherent encryption and robust lifecycle management means native Kubernetes secrets are often considered insufficient for highly sensitive data and production environments, prompting the need for more advanced solutions. To see secret consumption in action, we'll deploy a secret consumer app pod. This simple application is configured to read the API_key and DB_password from our app API key secret and output them to its logs as environment variables. After the pod starts, we can use kubectl logs to inspect its output. You'll see the decoded values of mysupersecretapiki and secured password printed, confirming that the application successfully retrieved the sensitive data. This demonstration highlights the ease of integrating secrets with your applications. However, it also underscores the point about base 64 encoding. Anyone with get secret permissions can easily decode and view the values.